Hi everyone, my name is Piotr and welcome to our webinar on Rust, WebAssembly and how we use both in ScyllaDB. I'm a software engineer at ScyllaDB, usually busy with the database core written in C++ and C*, our framework, but lately I also started pushing a little bit of Rust and WebAssembly here and there. First, let me start with a little intro to ScyllaDB. ScyllaDB is a distributed NoSQL database focused on high performance and scalability. It was originally modeled after Apache Cassandra and is compatible with its interface language CQL. And lately, we also added support for DynamoDB compatible API called Alternator. Now here's a quick snapshot of some of the industry game changers using ScyllaDB. As you can see, it's not just one industry, actually. Anyone looking to run a fast, highly available distributed database can go ahead and use us. You can start small and keep scaling. And if you don't see your logo on this list and have a great use case to share with us, just feel free to get in touch. This webinar consists of two parts. The first part covers our Rust driver, why it's cool, and and how it can be leveraged in other programming languages. And then I'll move to user-defined functions and user-defined aggregates based on WebAssembly, our new thing. Let's start with the driver. Our driver was born during a hackathon a few years ago. I think it's free by now. But it's grown to be a full-fledged open source project right now. We've actually already accepted quite a few open source contributions, and we already know that the driver is used in production in multiple environments. Well, mostly because these production users are very eager to report bugs very quickly to us. In any case, we had the advantage of writing the whole driver from scratch. So we started by including all our requirements in the design. The driver should be fully asynchronous, have ScyllaDB specific optimizations like shard awareness, where the driver is capable of sending requests to the specific CPU to be faster. Well, our driver was generally designed to be as fast as possible, but at the same time easy to use and extensible. And I really hope that by now we've met everyone's expectations. When creating an asynchronous driver or any library or project, there's a decision to make, a design decision. Should this library be runtime agnostic, or should it be built on top of a specific subsets of runtimes, or should you implement your own? Runtime, for people not familiar with the concept, is a library that's responsible for actually running your async functions by polling them. So that's how asynchronous is designed, and it's quite a fundamental decision to make. We picked Tokyo because it's the most popular one. It's also more likely that other applications that want to connect to ScyllaDB or Cassandra already use Tokyo anyway, which makes the adoption easier. Ideally, we would write the driver in a runtime agnostic way, but we judged that the ecosystem is not quite ready for it yet because Tokyo has lots of features that are hard to get in a generic environment. Now, we want the interface of our driver to be straightforward, but powerful at the same time. So many of the details can be configured, but we also provide the default values for everything that makes sense. For instance, when a user wants to establish a CQL session with ScyllaDB, the only required parameter is the address of one of the nodes, and that's it. A session is pretty much everything that the user needs to create to start communicating with the database and using it. And with the help of a session, it's possible to send requests and to receive results. Now, depending on the workload type, users might want to specify some technical details like custom number of connections to the database nodes. Our default establishes a single connection per shard per each node, but users are free to define any other combination that works for them and for their workloads. By the way, per shard connections are a ScyllaDB specific feature, but since our driver is built for Cassandra users as well, they can just set it up so it works fine. Now, one of our killer features in terms of performance is token-aware routing and shard-aware routing. Token-aware routing is something that is supported in our driver from the start, and it's a load balancing policy which computes token values from queries on the client side and tries to send the requests straight to the database node that owns this particular data. And our driver takes it even a step further. Once a request is ready to be sent, the driver will try to send it not only to the node that has the data, but directly to the CPU core, which owns this particular partition. And that translates to even better latency because data goes straight to the shard responsible for handling the request. And that's possible because by default, ScyllaDB Rust driver maintains a separate connection for each core, each CPU core that every node of your database cluster has, and keeps up-to-date topology information which says which data belongs where on which node. Now, a common recommended practice when using ScyllaDB is to prepare your queries in order to save CPU time spent on parsing SQL strings and lots of other redundant things. So in order to make the driver more ergonomic for the users, it is possible to use a caching session, which automatically takes care of preparing statements and re-preparing invalidated statements and everything like that. So you as a user don't have to even think about it. There is a really good blog post from a couple of years ago about prepared statements, and I encourage everyone to take a look at it. Now, next thing that we're quite proud of are observability tools. Firstly, the driver is integrated with a tracing crate in the Rust ecosystem, which provides a way of integrating multiple login environments. It can be printing to the logs, like printing the logs to your screen, or saving them on disk, or sending them to some external observability services like Grafana or Datadog, anything you imagine. And that's very useful for debugging and looking for bottlenecks, but also for more complex analysis, gathering various statistics, etc. Our driver also exposes a number of useful metrics on its own. For instance, how many requests were sent in each session, what was their latency, how many of them were successful, and many more. The driver is also capable of using this information to pick up nodes. It's actually an upcoming feature. Now we're also integrated with the SQL tracing mechanism. In SQL, the language that ScyllaDB and Cassandra supports, each query can be individually traced so that a detailed list of steps and their timestamps can be later investigated in search for performance regressions. Our driver fully supports query tracing, and its results can be simply printed to logs or saved for later analysis, or even stored somewhere for later, whatever you want. You can see on the slide that it is possible to deduce which step of your query took how many microseconds, how many nodes were contacted, how long it took for the database to actually fetch the data from disk, was the data already in cache, and so on. All in all, tracing output is full of very important details, which are quite invaluable for diagnosing potential performance issues. Especially if you're trying to hunt down which query takes so long and why. Now, now that we have a Rust driver that's quite fast and robust and secure and so on, we also have a big plan of replacing other drivers with bindings to our one true driver, the ScyllaDB Rust driver. A single centralized implementation of the drivers would make it way easier to maintain, and Rust's superior performance can speed up the existing solutions available in other languages like Python, Ruby, and other languages with dynamic typing, which generally tend to be slower on average. We actually already have a working proof of concept for replacing our C++ driver with Rust bindings. You can take a look under the link I showed on this slide. And some very initial work has also been done for implementing a new Python driver, which is based on a very nice PyO3 crate, a Rust project that provides seamless integration between asynchronous Python and asynchronous Rust. And it even has specialized Tokyo support, which we really appreciate, because that's what allows us to seamlessly integrate our driver with Python as well. The Python one is in a very early proof of concept stage, but it actually looks very promising. And support for more languages is also planned, but these are the first two that we picked. Now let's switch to the other part of the presentation, which is user-defined functions and user-defined aggregates powered by our new backend language, WebAssembly. Let's start with a short introduction to WebAssembly itself. WebAssembly is a format for executable code designed first and foremost to be portable and embeddable. And as its name suggests, it's a good fit for web applications, but it's not only that. It's generally a good choice for an embedded language, especially that it's also quite fast and isolated. And well, one of the core features of WebAssembly is isolation. Each module is executed in a sandboxed environment, separate from the host. And it can't do many things like accessing disks or networking and so on its own. And such a limited trust environment is really desired for an embedded language, because it reduces the risk of somebody running malicious code from within your project to take over your machines and things like that. Wasm is a binary format, but it also specifies a human readable text format called WebAssembly Text Format, and people also call it WAT. So what do we need WebAssembly for? What do we want to embed in ScyllaDB? Our first use case is user-defined functions, also known as their acronym UDF. This is a CQL feature that allows defining a function in given language and then using this function when querying the database. The function will be applied on the arguments by the database itself, and only then the results will be sent to the user. It's also possible to express nested calls and other more complex operations with UDF, as you can see here on the example slide. Now, user-defined functions are already cool on their own, but their most important purpose is enabling user-defined aggregates. These are custom accumulators which combine data from multiple rows into potentially complex outputs. User-defined aggregates consist of two functions, actually. One for accumulating the result for each argument, and one for finalizing the result and transforming it to the output type. On this slide, you can see an example of an aggregate function that computes the average length of all requested strings. So one function is used to accumulate partial results by storing the total sum of all lengths and total number of strings. And the finalizing function divides one by the other in order to return the result. In this example, the result is presented as an already rendered text. As you can see, the potential here is quite large because user-defined aggregates allow using the database queries in a quite more powerful way. For instance, gathering complex statistics or transforming whole partitions into different formats like JSON and so on. The built-in set of aggregates in ScyllaDB and in Cassandra is quite small because it basically only allows you to take an average or max or minimum or sum of some columns. So these user-defined aggregates are way more powerful, especially that you can combine values from multiple columns in various ways. So now that we know what user-defined functions and user-defined aggregates are, how one would even create a WebAssembly program if you want to use WebAssembly for that. First of all, modules, which is a kind of an entity in WebAssembly, can be coded directly in WebAssembly text format. It's not the most convenient way due to Wasm's limited type system and specific syntax, but it's of course possible. All you need for that is a text editor. C or C++ enthusiasts can compile their language of choice to Wasm with the Clang compiler. The binary interface is well defined and the resulting binaries are quite well optimized. We've tested that. Underneath, the code is compiled to WebAssembly with the use of LLVM representation for those who are curious. Rust also has the capability of producing Wasm output in its ecosystem. You can use Wasm32 target, which is already supported in the official build toolchain Cargo. As for other languages, there's also AssemblyScript, which is a TypeScript-like or JavaScript-like language, which compiles directly to WebAssembly. And AssemblyScript is especially nice for quick experiments because it's a scripting language. It's also the only language that was actually invented and designed with WebAssembly as a compilation target in mind, specifically. Still, Scylla has its own set of supported data types, like strings, integers, and so on. And these do not always have their identical counterparts in programming languages. Fortunately, the process for Rust can be automated in a very nice way by using a helper library that we provide. For example, here on the slide is a regular Rust function that uses only native Rust types, and this function conceptually transforms a list of strings into a single string, consisting of all the input strings separated by commas. Now let's take a look at how to modify this code so it can be compiled into a WebAssembly-based user-defined function which can actually run inside Scylla. And that's it. The only the only difference is this one line at the top. The macro you see here will automatically generate proper code, which translates all the types and makes the function ready to be used in ScyllaDB after it's compiled to WebAssembly. This is extremely convenient if you already have working code that does your application logic. And chances are that you just need to decorate your code with this single line, and then you can run it in ScyllaDB itself. ScyllaDB will run everything directly on the tables on the database nodes and return the results to you. Finally, Wasm-powered user-defined functions are already available in ScyllaDB, but in experimental mode. So don't hesitate and spin a test cluster and try it out. And here's how you can set your nodes up to enable this experimental feature, including WebAssembly for user-defined functions.
Great, thank you, Piotr. So hello, everyone again. We do have one last poll that we'd like to get from you. And just for a sense of scale, we'd like to understand how much data do you have under management in your own transactional database? Is it less than a terabyte, 1 to 10 terabytes, 10 to 100 terabytes, or more than 100 terabytes? So just pick the answer that matches, best matches your current data set. And we'll leave that up for just another minute or so. And then we can go on to Q&A. So now it's time to hear from you, our audience. So if you have questions for Piotr, please just use that Q&A button that's located on the bottom of your screen, a little bit to the right, to ask your questions. And we've already had some questions. So let's see what we have here. Piotr, we've got one that says, you mentioned that C++ and Python drivers will get rewritten to use the Rust driver. Are you also planning to support Go?
Well, eventually maybe, although Golang is a little tricky because it has its own kind of built-in asynchronous environment, its own system for running coroutines asynchronously. So I think it's going to be a little tough to come up with an implementation that's actually faster and better. But actually, Go would be next on our plate, at least for research and development purposes after we're done with the two.
Okay, great. And we'll let everybody know when that is available. Okay, it looks like we actually don't have more questions today. So thank you for that question. And we, just a reminder, we do have the recordings for the previous 2 sessions that we did. And so those we will send to you along with this one. And just also, if you have any, if you want to go to our last slide there, Pietra, just want to thank you all for joining us today. If there's any other topics that you'd like to hear, just let us know. Please join our Slack community if you aren't there already. We have thousands of your fellow database monsters on there, always talking, lots of good conversations there. So now, on behalf of Pietra, Merce, and myself, and all of us at ScyllaDB, we'd like to thank you for joining us today and enjoy the rest of your day. Bye-bye now.